Something quiet is happening in the sky. Not all at once, not loudly, but steadily. Over just a few days, several asteroids slipped past Earth. A newborn comet appeared where nothing had been before. And far beyond Mars, an interstellar traveler called 3I Atlas continues its silent approach. None of this is dangerous. There is no emergency. But the timing is unusual. And when many small events begin to line up, science does something very human. It slows down. It looks closer. And tonight, we do the same. Not to fear the sky, but to understand how busy it has always been, and why we are only now starting to notice. In the quiet routines of modern astronomy, most nights look very much the same. Telescopes scan the sky, computers sort through faint points of light, and scientists log small changes that usually fit into patterns they already understand. Space, for the most part, feels steady and predictable. But every so often, that calm rhythm shifts. In recent days, astronomers around the world began noticing something subtle but unusual. The number of detected objects moving through familiar regions of space started to rise. Not by a dramatic amount all at once, but enough to catch careful attention. Small asteroids, faint comets, and dim wanderers appeared in the data streams more often than expected, like distant lights slowly filling a dark horizon. This did not happen with alarms or flashing warnings. It came quietly, through routine reports and shared observations. One observatory would note a new near-Earth asteroid. Another would log a faint comet with a fresh glow. Space surveys that normally catalog a steady trickle of objects suddenly had a longer list to review. Each discovery on its own seemed ordinary. After all, astronomers find new objects every day. But together, the timing felt different. It was as if familiar pathways through the solar system had grown busier, not in a chaotic way, but in a gentle, noticeable swell. For people outside the world of astronomy, this kind of increase can sound dramatic. It's easy to imagine rocks rushing past Earth or threats lurking just beyond view. But inside the scientific community, the first reaction was calmer. Questions came before conclusions. Was this a real increase in objects, or simply a result of better detection? Had new telescopes come online, or had software updates made faint objects easier to spot? These are the kinds of explanations scientists always check first, because the sky has not suddenly changed just because we notice something new. Over the last decade, the tools we use to watch space have improved quietly and steadily. Wide-field surveys now cover larger portions of the sky each night. Cameras are more sensitive, able to pick up objects that would have gone unnoticed just a few years ago. Computers compare images faster and more accurately, spotting movement that once blended into the background. In many cases, a crowded sky is really a clearer sky, one where we are finally seeing what was always there. This possibility was at the top of every discussion as reports of new objects continued to arrive. Still, even with better tools, the clustering of discoveries drew interest. Some of the objects followed similar paths, moving through regions already known to be active. Others appeared in places that had been quiet for months. A few were moving faster or slower than expected, hinting at unusual orbits shaped long ago by gravity and chance. None of this meant danger, but it did suggest complexity. The solar system, often pictured as a neat set of paths around the sun, is in reality a living, shifting environment filled with leftovers from its birth. Asteroids and comets are not random intruders. They are part of the solar system's deep history. Asteroids are rocky fragments, many of them remnants from the early days when planets were forming. Comets are icy travelers, spending most of their lives far from the sun before drifting inward and growing a glowing tail. These objects move in families and streams, shaped by gravity from planets like Jupiter and Mars. When Earth passes through one of these streams, we sometimes notice more activity, not because space has changed, but because our position within it has. In recent days, Earth's location in its orbit placed us in a better position to see certain objects. Some asteroids became easier to detect because of the angle of sunlight reflecting off their surfaces. A newborn comet flared briefly as it warmed for the first time, making itself visible before fading again. Even interstellar objects, which come from beyond our solar system, can appear during windows when their paths line up just right with our instruments. These moments can make space feel suddenly busy, even though the movement itself is slow and steady. What makes this period especially interesting is how many different types of objects appeared close together in time. Near-Earth asteroids, distant comets, and faint wanderers from deep space all showed up in observation logs within days of each other. For scientists, this is less a cause for concern and more an opportunity. Each object carries information about where it came from and how it has traveled. Together, they offer a snapshot of the invisible traffic that moves through our neighborhood every day. For viewers watching from home, especially late at night, this idea of a crowded sky can feel unsettling. Space is often thought of as empty and quiet. The thought that it is actually filled with countless moving bodies can challenge that sense of calm. But there is another way to look at it. The fact that we are noticing these objects means our understanding is growing. We are not more vulnerable because we see more. In many ways, we are safer, because knowledge replaces surprise. Astronomers have long known that space is busy. Millions of asteroids orbit the Sun, most of them far from Earth. Comets come and go on schedules that stretch over decades or even centuries. Interstellar visitors pass through rarely, but they remind us that our solar system is not sealed off from the rest of the galaxy. What feels new is not the activity itself, but our awareness of it. We are finally watching closely enough to see the slow dance unfold. As reports continued, scientists shared data, compared notes, and refined their models. No single object stood out as dangerous. No paths pointed toward Earth in a way that caused alarm. Instead, the picture that emerged was one of motion and connection. The solar system is not a static diagram in a textbook. It is a flowing environment, shaped by gravity, time, and countless past events. The recent increase in detection simply lifted the curtain a little higher. For those listening now, this moment invites a quiet shift in perspective. The sky above us is not suddenly threatening or unstable. It is active in a way it has always been. Rocks and ice move along ancient routes, guided by forces older than Earth itself. We are not standing still beneath a storm of chaos, but resting within a system that has been moving this way for billions of years. Seeing more of it does not mean something is wrong. It means we are paying closer attention, noticing details that were once hidden, and learning to recognize the gentle, constant motion that surrounds our world every night. In the quiet hours of recent nights, while most people were asleep, several small asteroids slipped past Earth without a sound. They did not flash brightly in the sky, and they did not trigger alarms or headlines for most of the world. These objects moved through space calmly and predictably, following paths that scientists had already mapped with care. To the average person, nothing seemed different. The ground stayed still, the sky looked the same, and life continued as usual. Yet high above, in the vast space around our planet, these visitors were passing by, reminding us how active our neighborhood really is. Near-Earth asteroids are far more common than many people realize. Space around our planet is not empty. It is filled with rocks of many sizes, from tiny pebbles to large mountain-sized bodies, all circling the Sun. Earth moves through this region every day, sharing space with countless objects that formed long ago when the solar system was young. Most of these asteroids stay far away, but some pass close enough to be noticed by telescopes designed to watch the sky with patience and precision. In recent days, astronomers tracked a small wave of these near-Earth asteroids as they passed by at safe distances. None of them were large enough to cause concern, and none were on paths that posed any danger. Still, seeing several pass in a short time can feel surprising, especially for people who do not often think about how dynamic space really is. The truth is that this kind of activity is normal. It happens more often than the news suggests, simply because many passes are too quiet and too safe to be considered dramatic. Each of these asteroids moved fast, sometimes faster than a speeding bullet, yet from Earth they appeared slow and steady when tracked through instruments. Their speed comes from gravity, from the long pull of the Sun and the subtle nudges of planets over millions of years. These forces guide asteroids along invisible roads through space, roads that cross Earth's orbit again and again. When scientists say an asteroid passed close, that distance is usually still hundreds of thousands or even millions of miles away. What makes these passes interesting is not danger, but frequency. When people hear that several asteroids passed Earth in a single week, it can sound unusual. In reality, many small asteroids pass by every month, and some pass by every week. We notice them more now because our ability to detect them has improved. Modern telescopes scan the sky every night, capturing faint points of light that older instruments would have missed entirely. What feels like a sudden wave is often a wave of awareness rather than a wave of new objects. Many of these asteroids are only a few dozen feet wide. If one entered Earth's atmosphere, it would likely burn up harmlessly, creating a brief streak of light across the sky. Larger ones are tracked carefully, but even then, the odds of impact are extremely low. Scientists calculate orbits years, decades, and sometimes centuries into the future, using careful math and constant observation. This allows them to say with confidence when an object will pass safely by, long before it ever gets close. The quiet nature of these recent passes is important. There were no sudden changes in course, no unexpected accelerations, and no mysterious behavior. Each asteroid followed a path that made sense based on what we know about gravity and motion. This steadiness is comforting, even if it goes unnoticed. It shows that the system we live in, while busy, is also orderly. Objects move according to rules that can be studied, understood, and predicted. Sometimes people imagine space as either completely empty or full of sudden threats. The reality lies somewhere in between. Space is busy, but not chaotic. Near-Earth asteroids are part of a steady flow, like leaves drifting past a riverbank. Most pass by without ever touching the shore. A few are interesting to watch, and a very small number are studied closely, not because they are dangerous, but because they help us understand how the solar system works. When astronomers detect a near-Earth asteroid, they often observe it for days or weeks. Each observation refines its path, reducing uncertainty and improving future predictions. This careful process turns unknown objects into well-understood travelers. What begins as a faint dot becomes a mapped orbit, a known story, and eventually just another entry in a long catalogue of objects that share our space. The recent cluster of asteroid flybys also highlights how global this effort is. Telescopes around the world work together, passing data from one time zone to another. When night ends in one place, it begins somewhere else, allowing continuous tracking. This quiet cooperation happens every day, without drama, ensuring that nothing large goes unnoticed for long. For people over 30, many of whom grew up before constant space news, this level of monitoring may feel new. Decades ago, only the largest objects were tracked, and many small asteroids passed by unseen. Today, we see more not because space has changed, but because we have. Our tools are better, our coverage is wider, and our attention is sharper. There is also a gentle lesson in how calmly these events unfolded. No sirens sounded. No urgent warnings were needed. Life on Earth went on, while above us, space carried out its usual motions. This contrast between cosmic movement and human stillness can feel grounding. It reminds us that many things happen beyond our awareness, and most of them do not require fear or action. As these asteroids moved away from Earth, they continued their long journeys around the Sun. Some will not return near us for many years. Others may pass again sooner, still harmless, still watched. Their brief visits are like quiet reminders that Earth is part of a larger system, one that is always in motion, always changing, yet rarely threatening in the ways our imagination sometimes suggests. The wave of near-Earth asteroids was not a warning, and it was not a sign of danger. It was simply a moment when the ongoing activity of space became slightly more visible than usual. For those who study the sky, it was another calm week of observation and calculation. For everyone else, it passed unnoticed, like so many things that happen quietly above us, night after night, as the Earth continues its steady path around the Sun. Out in the quiet reaches of space, far beyond the bright paths of the planets, countless small bodies drift in darkness. Most of them are invisible, frozen, and silent, moving so slowly and reflecting so little light that even our most powerful telescopes barely notice them. Every so often, though, one of these ancient travelers begins a journey inward, pulled gently by gravity toward the warmth of the Sun. When that happens, something special occurs. A newborn comet is not truly new in age, but it is new to us, newly awakened after spending billions of years locked in deep cold, unchanged since the earliest days of the solar system. This recent discovery began quietly, as many discoveries do. A faint smudge appeared in telescope images, barely standing out from the background of stars. At first, it looked like a weak point of light, easy to dismiss as noise or a distant galaxy. But as astronomers tracked it night after night, they noticed something unusual. The object was moving, slowly shifting its position against the fixed star field. That motion told a simple but important story. This was not a star, and not a galaxy. It was something much closer, something belonging to our solar neighborhood, beginning its long descent toward the Sun. As the object moved closer, sunlight began to touch its surface for the first time in an unimaginable span of time. The surface of a comet is a mixture of ice, dust, and rocky material, often described as a dirty snowball. In the deep cold of space, these materials remain solid and quiet. But sunlight changes everything. Even at great distances, the sun's energy is enough to warm the outer layers just slightly. When that happens, ice does not melt into water the way it does on Earth. Instead, it turns directly into gas, a process called sublimation. This gentle release of gas lifts dust from the surface, creating a glowing cloud around the comet known as a coma. For astronomers, seeing a coma form is like watching a long silent object take its first breath. The newborn comet begins to glow, not because it produces light of its own, but because sunlight reflects off the released gas and dust. This glow can increase quickly, sometimes over just a few days, making an object that was once invisible suddenly stand out in the night sky. It feels dramatic, but it is also completely natural, following physical laws that have been at work since the solar system formed. What makes a newborn comet especially fascinating is its history. Many of these objects come from regions far beyond the planets, such as the Kuiper Belt or the distant Oort cloud. These areas are cold storage zones, filled with leftover building blocks from the formation of the Sun and planets. Because they have stayed so far away, these comets are like time capsules. Their ice still contains trapped gases from the early solar nebula, and their dust holds clues about the materials that once swirled around the young Sun. When a comet like this becomes active, it gives scientists a rare chance to study ancient matter without ever leaving Earth. As observations continued, astronomers measured the brightness of the comet and how quickly its coma expanded. These details help reveal what the comet is made of and how strong its activity is. Some newborn comets flare up suddenly, releasing large amounts of gas in short bursts. Others wake more slowly, building their glow over weeks or months. This particular comet showed signs of steady activation, suggesting that its surface layers were rich in volatile ices that respond easily to sunlight. That behavior tells a quiet story of composition, temperature, and age, all written in light. To the public, the idea of a new comet can sound dramatic, even unsettling. Comets are often tied to old myths and stories, seen as omens or signs of change. In reality, they are gentle travelers. Their paths are predictable, their mass small, and their behavior well understood. This newborn comet posed no threat to Earth. It passed far away, following an orbit shaped long ago by gravity alone. Yet its appearance still captured attention, because it reminded us that the solar system is not static. It is active, dynamic, and constantly evolving. For scientists, the timing of this discovery felt especially interesting. Around the same period, astronomers were also tracking near-Earth asteroids, monitoring interstellar visitors like 3I Atlas, and studying increased activity linked to the Sun's current cycle. Each event on its own was explainable. Together, they created a sense that the sky was busier than usual. The newborn comet fit into this broader picture, not as a cause of concern, but as another piece of evidence that our ability to detect faint objects has improved dramatically. Modern telescopes are far more sensitive than those used even a decade ago. Automated surveys scan the sky every night, comparing new images with old ones to spot changes. This technology means we are discovering comets earlier in their journeys, sometimes before they show much activity at all. In the past, a comet like this might have gone unnoticed until it was much closer to the Sun and much brighter. Today, we see the awakening almost from the start, watching the process unfold in slow motion. There is something deeply calming about this process when viewed with patience. A newborn comet does not rush. It follows a path set by gravity, responding gently to sunlight, shedding material grain by grain. Its glow grows, then fades, leaving behind a thin trail of dust that will slowly disperse into space. Nothing about it is sudden or violent on a human timescale. It reminds us that even dramatic-looking events in the sky are often the result of slow, steady processes playing out over millions of years. As astronomers continue to observe this comet, they gather spectra, measuring the light it emits to identify specific gases like water vapor, carbon dioxide, and carbon monoxide. Each detection adds to a growing understanding of how comets differ from one another. Some are rich in certain compounds, others poor. Some are pristine, others have made many trips around the Sun and lost much of their original ice. This newborn comet, still early in its active phase, offers especially clean data, before solar heating alters its surface too much. For viewers at home, the story of a newborn comet can be taken in quietly, without fear or urgency. It is a reminder that the night sky is alive with motion, even when it looks calm and unchanged. Objects come and go, brighten and fade, following rules that scientists work hard to understand. There is comfort in knowing that these events are expected, monitored, and studied with care. As the comet continues its approach, its glow may increase, then eventually diminish as it either passes the sun or retreats back into the cold. Either way, its brief moment of visibility leaves behind knowledge. Data collected now will be compared with future comets, building a clearer picture of how these ancient objects behave. Each discovery adds another soft chapter to the long story of our solar system, a story that unfolds slowly, patiently, and without urgency, inviting us to watch, to learn, and to rest while the universe carries on its quiet work. 3I Atlas did not form around our sun. It began its journey far away, around another star that we may never see clearly. Long before Earth had cities, or oceans filled with life, this object was already moving through deep space, carried by gravity alone. It traveled for ages through cold darkness, untouched and silent, until one quiet moment when its path crossed ours. When astronomers first noticed it, they quickly realized this was not just another comet or asteroid. Its speed, direction, and chemistry all pointed to the same calm conclusion. This object came from beyond our solar system. Objects like this are called interstellar travelers. They are rare visitors that pass through star systems without belonging to them. Most of what we see in the sky formed from the same spinning disk of gas and dust that became our sun and planets. Interstellar objects are different. They are outsiders. They were shaped by another sun, another environment, another long history. Because of that, they carry clues about places far beyond our reach. That is why scientists pay close attention when one appears, even if it poses no danger at all. 3I Atlas was detected as a faint point of light moving in a way that did not match normal solar system objects. Astronomers noticed its path was too steep, too fast, and too direct. Gravity calculations showed that the sun was not pulling it into a long orbit. Instead, the sun was only bending its path slightly, like a stone passing through a stream. This told researchers that 3I Atlas was only passing through. It would not stay. It would not return. It was simply visiting, moving on a one-time journey through our neighborhood. As it approached the inner solar system, sunlight began to warm its surface. Frozen gases and ice that had been locked in place for millions or even billions of years started to release gently into space. This created a soft glow around the object, known as a coma. To the eye, it looked dramatic, even mysterious, but to scientists it was familiar behavior. This is what happens when cold material meets warmth after a long time. The glow did not mean activity or intent. It was simply physics doing what physics always does. What made 3I Atlas especially interesting was its direction. Its path brings it closer to Mars than many other known interstellar visitors. Mars sits at a quiet crossroads in our solar system. It is far enough from the sun to remain calm, yet close enough to be well studied by orbiters and telescopes. As 3I Atlas moves inward, Mars becomes an important reference point. Scientists can use its position to better track the visitor's speed, shape, and composition. This makes the encounter valuable, even if nothing dramatic happens. Mars itself is not in danger. The distance between the planet and 3I Atlas remains vast. Space is incredibly large, and close in space still means millions of miles apart. The idea of danger often comes from how images are shown or how numbers feel without context. In reality, the encounter is gentle and distant. What matters is not the closeness, but the chance to observe an object from another star system using modern tools. Interstellar objects remind us that our solar system is not sealed off. It is part of a larger galaxy filled with motion. Stars orbit the center of the Milky Way. Gas clouds drift and collapse. Old systems break apart, and their leftovers scatter. Over time, pieces of one system can wander into another. 3I Atlas is likely one such fragment, set loose long ago by gravitational shifts or stellar movement. It does not carry messages or meaning. It carries history. For scientists, history matters. By studying the light reflected from 3I Atlas, they can learn what it is made of. Different materials reflect light in different ways. Ice, carbon, rock, and metal all leave subtle fingerprints. These clues help researchers compare this object to ones formed near our sun. Similarities suggest shared processes across the galaxy. Differences hint at new conditions, new chemistry, and new ways planets and debris can form. As 3I Atlas continues toward Mars, telescopes on Earth and in space quietly track its motion. There is no rush, no alarm, only careful observation. Data is gathered night after night, refined and checked. Models are updated. Predictions are improved. This steady process is how science works best, especially with rare events that may not happen again for decades. For people watching from Earth, it can feel strange to know that something from another star is passing nearby. It challenges the idea that our world is isolated. Yet there is comfort in understanding how common motion really is. Space is not empty. It is full of slow journeys, long paths, and silent travelers like 3i Atlas. Most pass unnoticed. A few are seen. None are personal. Mars has long been a focus of human attention. We send machines there. We map its surface. We imagine future explorers walking its soil. Seeing an interstellar object pass near Mars adds another layer to that story. It reminds us that Mars, like Earth, exists within a moving system that interacts with the wider galaxy. The planet is not just a destination. It is a marker within a flow of cosmic traffic. There is no special alignment, no hidden message in the timing. 3i Atlas is not arriving because something is happening. It is arriving because gravity placed it on this path long ago. The fact that we are here to see it now is a coincidence shaped by technology and curiosity. 100 years ago, it would have passed unseen. 100 years from now, other visitors may do the same, watched by tools we have not yet imagined. As the object continues its calm passage, it will eventually leave our solar system behind. The sun's pull will fade. Mars will drift away in the background. 3i Atlas will return to the dark between stars, carrying with it a tiny influence from our system, but unchanged in purpose. Its journey will continue, long after attention shifts elsewhere. In moments like this, science does not rush to conclusions. It observes, measures, and waits. Interstellar travelers do not mean danger or destiny. They mean connection. They show that the processes that shaped our world are not unique. They happen everywhere, quietly and endlessly, across the galaxy. Watching 3i Atlas move closer to Mars is not about fear or excitement. It is about understanding motion, distance, and time, and about noticing that even in the vastness of space, paths sometimes cross, gently and without consequence. Interstellar objects are different from the space rocks we usually hear about because they were not born here. Most asteroids and comets formed from the same spinning cloud of gas and dust that became our Sun, our planets, and the smaller bodies that still move between them. They share a common family history. Interstellar objects do not. They come from entirely different star systems, places with their own suns, their own planets, and their own long histories. When one of these visitors drifts into our solar system, it brings with it a quiet record of conditions far beyond our reach. To understand why this matters, it helps to imagine how our own solar system formed. Billions of years ago, a cloud of gas collapsed under gravity. Most of it became the Sun, and the rest flattened into a disk where planets slowly grew. Leftover pieces became asteroids and comets. These objects are like time capsules, but they all come from the same neighborhood. Interstellar objects, on the other hand, formed around other stars, possibly in environments very different from ours. Some may come from colder regions, others from hotter or more chaotic systems, shaped by forces we can only guess at. One of the first things scientists notice about interstellar objects is their speed and direction. Objects that belong to our solar system usually follow predictable paths around the Sun. Their orbits are shaped by long-term gravitational relationships. Interstellar objects arrive on steep, fast paths that do not loop back around. They come in once and then leave, carrying on toward deep space. This tells scientists they are not bound to the Sun. They are passing through, like travelers stopping briefly before continuing on their journey. Their shapes can also be unusual. While many asteroids are roughly round or irregular but compact, some interstellar objects appear stretched, flattened, or oddly shaped. These shapes may reflect violent histories, such as close passes near other stars or collisions in distant systems. In some cases, the way light reflects off them suggests surfaces that do not behave like the rocky or icy bodies we know well. This raises gentle questions about how different star systems shape the materials around them. Another key difference lies in their chemistry. When sunlight warms an object in space, it can release gases and dust. By studying this faint glow, scientists can learn what the object is made of. Comets from our solar system often release water vapor, carbon dioxide, and other familiar compounds. Interstellar objects may show different mixtures, or in some cases, surprisingly little activity at all. These differences hint at conditions around their home stars, such as temperature, radiation, and the makeup of the original gas cloud that formed them. Interstellar objects also challenge our expectations about age. Many comets in our solar system have been altered by repeated passes near the Sun. They lose material over time and change slowly. An interstellar object may be visiting a star like ours for the very first time after drifting through cold space for billions of years. Its surface may be more pristine, preserving clues from an earlier era of the universe. This makes each one a rare scientific opportunity. There is also the question of how these objects are set free. For an object to leave its home system, something powerful must happen. It may be nudged by a giant planet or thrown outward by a close stellar encounter. This means interstellar objects carry the story of movement and change on a much larger scale. They are reminders that star systems are not closed worlds, but dynamic places where material can be exchanged across vast distances. When scientists compare interstellar objects to local ones, they are not looking for danger or drama. They are listening carefully, trying to understand how common certain features are across the galaxy. Do most systems make comets like ours, rich in ice and dust? Or are there many systems that produce objects that behave very differently? Each visitor helps refine these questions. The discovery of multiple interstellar objects in a relatively short time also suggests that space between stars may be more crowded than we once thought. For a long time, scientists assumed such encounters would be extremely rare. Now, improved telescopes and better tracking methods are revealing faint travelers that might have passed unnoticed before. This does not mean the universe suddenly changed. It means our ability to see has improved, allowing us to notice what was always there. Interstellar objects also encourage a broader view of our place in space. They remind us that the materials that built Earth are not unique. Similar processes happen around countless stars. At the same time, the differences we observe show that each system has its own character. Some may be calm, others turbulent. Some may produce stable planets, others flinging debris into interstellar space more often. The way scientists study these visitors is careful and patient. They track their paths, measure their light, and compare data across observatories worldwide. There is no rush, because these objects are not threats. They are messengers. Each one offers a short window of time to gather information before it moves on. The work is quiet, detailed, and focused on understanding rather than reaction. For people watching from Earth, the idea of something arriving from another star system can feel emotional. It touches on curiosity, wonder, and sometimes unease. But at its core, the science is reassuring. These objects follow the same laws of physics as everything else. They move, reflect light, and respond to gravity in ways we can predict and measure. Their mystery is not a cause for fear, but an invitation to learn. As more interstellar objects are found, patterns may begin to emerge. Scientists may notice similarities that point to common processes across the galaxy. Or they may find surprising variety, showing just how diverse star systems can be. Either outcome adds to a calmer, deeper understanding of the universe. In the end, what makes interstellar objects different is not that they are dangerous or strange in a threatening way. It is that they carry stories from places we cannot yet visit. They are quiet reminders that our solar system is part of a much larger family of stars, all moving together through space, occasionally sharing pieces of their past as they pass by. Mars has always held a special place in how we understand space, not because it is mysterious or dangerous, but because it sits in a very useful position between worlds. When scientists track objects moving through the solar system, they rely on steady reference points, and Mars provides one of the best. It orbits farther from the Sun than Earth, but not so far that it disappears into the slow, distant rhythms of the outer planets. Its path is well known, its motion predictable, and its location stable in a way that makes it ideal for measuring how other objects move nearby. In simple terms, Mars acts like a marker on a long road. When something unfamiliar enters the neighborhood, it helps to know exactly where that road sign is. By watching how an object passes relative to Mars, astronomers can better understand its speed, direction, and origin. This is especially important when tracking unusual visitors, like newly discovered asteroids, fresh comets, or objects that do not belong to our solar system at all. Mars gives scientists a middle ground, a calm reference point that helps turn scattered observations into a clear picture. Mars also sits close to a boundary that matters a great deal in space science. Inside Mars' orbit are the inner planets, including Earth, where rocky worlds circle quickly and sunlight is strong. Beyond Mars lies the asteroid belt, a wide region filled with countless rocks left over from the early days of the solar system. Because Mars orbits near this boundary, it naturally becomes a checkpoint for objects moving inward or outward. When something crosses the region near Mars, it often signals a shift, like a traveler passing from one climate into another. This position makes Mars especially valuable when astronomers notice an increase in activity. If several objects appear around the same time near Mars' orbit, it suggests patterns that might otherwise be missed. Some objects may be nudged inward by gravity, while others may be making their first pass through the inner solar system. Mars helps scientists tell the difference. Its steady presence allows them to measure subtle changes and compare one object's path to another with greater confidence. Another reason Mars matters so much is visibility. Mars is one of the most observed planets in the solar system. Space agencies have sent orbiters, landers, and rovers there for decades. Because of this, Mars is surrounded by a web of instruments constantly collecting data. Telescopes on Earth track it, spacecraft near it monitor space conditions, and long-term models describe its motion in great detail. When something passes near Mars, it often passes through an area that is already being watched closely. This constant attention turns Mars into a kind of listening post. When an unfamiliar object approaches, scientists can compare new data with years of past observations. Even small changes stand out. A slight shift in brightness, an unexpected turn, or an unusual speed becomes easier to detect when measured against such a well-known background. Mars does not just sit there silently, it quietly anchors our measurements. Mars also plays a role in understanding gravity. Every planet shapes space around it through its gravitational pull, and Mars is no exception. While its gravity is weaker than Earth's, it is strong enough to gently influence passing objects. By studying how an object's path changes as it moves near Mars, scientists can learn about both the object and the planet. These interactions help refine models of how gravity works across the solar system, especially in crowded regions. For interstellar visitors like 3i Atlas, Mars becomes even more important. Objects from other star systems arrive with paths that do not match the usual patterns of comets and asteroids born around our Sun. When such an object passes near Mars, scientists can see how its trajectory differs from familiar bodies. Mars acts as a comparison point, helping confirm that the object truly came from outside and was not simply disturbed from a distant orbit closer to home. There is also a human element to Mars' importance. For many people, Mars feels closer than the rest of space. It has seasons, a day length similar to Earth's, and a surface we have seen in detail. When scientists talk about something approaching Mars, it feels easier to imagine. This helps communication and understanding. Mars becomes a bridge between abstract space data and human intuition, allowing complex movements to be explained in clear, simple ways. Mars' role as a marker is also tied to timing. Because its orbit is well understood, astronomers can use it to predict when and where an object will appear next. If something passes near Mars today, models can estimate where it will be weeks, months, or years from now. This predictive power is essential for calm, careful observation. It removes urgency and replaces it with planning, allowing scientists to observe without alarm. As space becomes more closely watched, Mars continues to help sort noise from meaning. Telescopes now detect more objects than ever before. Many are small, faint, and harmless, but together they can feel overwhelming. Mars provides structure in this growing flow of information. It helps scientists group objects, identify trends, and understand which movements are routine and which deserve closer attention. There is also a deeper reason Mars matters as a marker, one tied to history. For centuries, humans watched Mars move across the sky and learned how planets travel. Those early observations helped uncover the laws of motion that still guide space science today. In that sense, Mars has always been a teacher. Its role in modern astronomy continues this tradition, quietly guiding understanding as new discoveries appear. When astronomers speak calmly about objects passing near Mars, they are not suggesting danger. They are describing a useful point of reference, a familiar place in a vast and changing system. Mars helps turn surprise into knowledge. It allows scientists to say not just that something is happening, but where, how, and why. This clarity is what keeps exploration steady and measured. As more objects are discovered and tracked, Mars remains where it has always been, moving along its known path, offering context and scale. It does not rush. It does not hide. It simply marks time and space, helping each new discovery find its place in a larger story. Mars has always captured human imagination. It glows quietly in our night sky, steady and familiar, a red point that ancient cultures watched long before telescopes existed. Because of that long connection, any suggestion that something might threaten Mars can feel unsettling, even if the science tells a calmer story. When people hear that new objects are moving through the inner solar system, and that an interstellar visitor like 3I Atlas is passing near the region of Mars, it is natural for the mind to wonder whether the planet could be at risk. This question has been asked many times in recent weeks, and scientists have answered it carefully, clearly, and with confidence. The short answer is reassuring. Mars is not in danger. Neither 3I Atlas nor the cluster of recently observed asteroids and comets is on a path that would bring them anywhere close to striking the planet. Astronomers track these objects with extreme precision, measuring their positions night after night and calculating their future paths using well-tested models of gravity and motion. These calculations are not guesses. They are based on decades of observation, physics that has been confirmed again and again, and computer simulations that account for the pull of the sun, the planets, and even smaller influences like solar radiation. When scientists say that an object will not hit Mars, they are not offering comfort based on hope. They are sharing conclusions drawn from thousands of data points. Each object's orbit is mapped in 3 dimensions, showing not just where it is now, but where it will be months or even years into the future. In the case of 3I Atlas, its path through the solar system is steep and fast, angled in a way that carries it through and back out into interstellar space. Mars happens to be nearby in a general sense, but in cosmic terms, nearby still means millions of miles apart. Mars itself moves along a predictable orbit, circling the Sun once every 687 Earth days. Its position at any moment is well known, as are the gravitational influences acting upon it. For an object to threaten Mars, it would need to be on a very precise collision course, one that aligns not only in space but also in time. None of the newly observed objects meet those conditions. Their trajectories simply do not intersect with Mars's path in a meaningful way. It is also worth remembering that Mars has endured far more dramatic events in its long history. Billions of years ago, during the early days of the solar system, impacts were common. Large asteroids and comets struck the planet, shaping its surface and leaving behind the craters we still see today. Those events occurred during a chaotic era when objects were far more numerous and orbits were less settled. Today's solar system is much calmer. While small objects still pass through, major collisions are rare, and when something unusual does appear, it is quickly noticed. The idea that Mars could be threatened often comes from how these stories are presented. Words like wave, cluster, or multiplying objects can sound alarming, even when the objects involved are small and widely spaced. In reality, space is vast. Even when astronomers detect many objects in a short time, those objects are usually separated by enormous distances. They are not traveling together like a swarm of birds. They are simply being discovered around the same time, often because new surveys and better instruments are scanning the sky more effectively than ever before. Mars, in particular, benefits from this improved attention. Because it is a target of ongoing exploration, both from orbiting spacecraft and from rovers on its surface, its surrounding space is watched closely. Any object passing near Mars is of interest, not because it is dangerous, but because it offers a chance to test predictions and refine models. Space agencies and observatories work together, sharing data openly, so that potential risks are evaluated from multiple perspectives. Another reason scientists are confident is that objects like 3I Atlas behave in ways that are consistent with natural physics. Its brightness, speed, and path all match what is expected from an interstellar object moving through the Sun's gravity. There are no sudden changes in direction, no unexplained accelerations, and no signs of interaction with Mars beyond a distant gravitational influence that is too weak to matter. Mars's gravity, while significant for its moons and nearby spacecraft, is not enough to pull in a fast-moving visitor passing far away. The same applies to the smaller asteroids detected near Earth and Mars's orbital region. These bodies are often only tens or hundreds of meters across, and they pass quietly, unnoticed by anyone except automated surveys. Their paths are catalogued, their risks assessed, and then they are added to a growing database of known objects. Most will never be seen again once they fade into the darkness, continuing their journeys without incident. It can be comforting to know that scientists are not waiting for something to go wrong before acting. Planetary defense is a proactive field. Even though Mars is not currently threatened, researchers study what would happen if a future object did approach too closely. They run simulations, test detection systems, and explore deflection techniques, not out of fear, but out of preparation. This work benefits not just Earth, but our understanding of the entire inner solar system. Mars serves as a kind of checkpoint in these studies. Its position between Earth and the asteroid belt makes it a useful reference for tracking objects moving inward from the outer regions. When something passes near Mars, it helps scientists validate their models and improve their ability to predict future motion. In that sense, Mars is not a target, but a tool, a stable marker against which change can be measured. Public concern often fades once these explanations are shared, but the initial worry reveals something important about how people relate to space. We care about Mars because it feels close to us, both physically and emotionally. It is the planet we dream of visiting, studying, and perhaps one day settling. Hearing that it might be in danger touches those hopes. The calm response from science does not dismiss that feeling, but gently places it in context. There is a quiet confidence in the way astronomers talk about these events. They do not rush to conclusions or dramatize uncertainty. Instead, they describe what they see, explain what it means, and acknowledge what is still unknown without letting that uncertainty grow into fear. In the case of Mars, the message has been consistent. The planet is safe. The objects passing through are being watched. The solar system, while active, is behaving exactly as physics predicts. As 3I Atlas continues its journey and the recently discovered asteroids move on, Mars will keep circling the Sun, unchanged and undisturbed. Spacecraft will continue to orbit it, rovers will keep exploring its surface, and telescopes on Earth will keep tracking the quiet motion of objects against the stars. The story unfolding above us is not one of danger, but of observation and understanding, of a solar system that is dynamic yet stable, and of a scientific community that is alert, patient, and deeply aware of where real risks lie and where they do not. When several events happen close together in time, our minds naturally lean forward and try to connect them. This is not a flaw or a mistake. It is part of how the human brain has worked for thousands of years. Long before modern science, noticing patterns helped people survive. Seeing clouds gather before rain, watching animals move before a storm, or sensing changes in the seasons allowed early humans to prepare. Pattern recognition became one of our strongest tools, and even today it works quietly in the background of our thoughts. When we see several space objects appear in the news at once, or hear about asteroids, comets, and interstellar visitors arriving within days of each other, the same instinct wakes up and starts asking questions. The problem is that the universe does not always follow the neat stories our minds prefer. Space is not organized around human attention. Objects move on paths that were set millions or even billions of years ago, guided by gravity, momentum, and chance. When one object appears after another, it often feels meaningful, as if something has changed or begun. But in reality, many of these objects were always there, quietly moving through dark regions where we simply could not see them. The moment we notice them can feel dramatic, even though nothing about their journey has changed. Modern astronomy has made this effect stronger. Telescopes are more powerful than ever before, and automated surveys now scan the sky every clear night. These systems do not sleep, and they do not blink. They find faint objects that would have been invisible just a decade ago. As detection improves, discoveries naturally increase. To the human mind, this can feel like a sudden surge, as if the sky has grown more crowded overnight. But much of what we are seeing now has always been there, waiting for our tools to catch up. There is also the way information reaches us. News spreads faster than light once did in old science fiction stories. A discovery made in one country is shared across the world in minutes. Social media and online headlines group unrelated events together simply because they happen close in time. A near-Earth asteroid, a new comet, and an interstellar visitor may each deserve attention on their own, but when presented together, they can feel connected even if they are not. Our brains are very good at filling in gaps, even when no real link exists. This tendency is called pattern seeking, and it is deeply human. We do it with numbers, with stories, and with history. When we look back at the past, we often arrange events into clean narratives with clear causes and effects. In real time, life is messier. Space is even more so. Objects move independently, each following its own rules. Some are leftovers from planet formation. Others are fragments from ancient collisions. A few, like interstellar objects, come from places far beyond our sun's influence. The fact that we notice several of them at once does not mean they are acting together. Fear can amplify this effect. When something feels unknown, the mind looks harder for meaning. Interstellar objects sound mysterious because they come from outside our familiar system. The word alone carries a sense of distance and uncertainty. When combined with other discoveries, it can feel like the beginning of something larger, even threatening. This is not because danger is real, but because uncertainty invites imagination. The brain prefers a story with a cause over randomness, even when randomness is the more accurate answer. Scientists are aware of this tendency, and they work carefully to avoid being misled by it. In astronomy, data is compared over long periods of time. Researchers look at years, decades, and even centuries of records. When patterns are real, they repeat consistently and follow physical rules that can be tested. When patterns are illusions, they fade when viewed from a wider angle. A cluster of discoveries in 1 month may look dramatic, but spread across 10 years, it often blends into a steady background of normal activity. Another important factor is selection. We notice what stands out and ignore what feels ordinary. Hundreds of small space objects pass through the solar system every year without headlines. They are too faint, too distant, or too predictable to catch attention. When one object behaves a little differently, or arrives from an unusual direction, it becomes news. This does not mean space has suddenly changed. It means our spotlight has shifted. The illusion forms when we mistake attention for importance. There is comfort in understanding this. It reminds us that the universe is not suddenly becoming unstable or crowded. It has always been active, always moving, always full of quiet motion. What has changed is our ability to see and measure it. As our tools improve, our picture of space becomes richer and more detailed. That richness can feel overwhelming at first, like stepping into a busy city after years in a quiet town. With time, the movement becomes familiar, even calming. The idea that events must be connected can also come from our love of stories. Stories have beginnings, middles, and endings. They move toward meaning. Space does not. It unfolds without concern for narrative structure. An asteroid does not know another asteroid exists. A comet does not arrive on cue. An interstellar object does not announce its presence. They simply move, following paths shaped by forces older than Earth itself. When we try to fit them into a single story, we are really telling ourselves something about how we understand the world. Recognizing the illusion of patterns does not mean dismissing curiosity. Curiosity is what drives discovery. It means holding curiosity gently, without letting it turn into fear or false certainty. It means asking questions while accepting that some answers are simple and unsatisfying. Sometimes events cluster by chance. Sometimes detection improves. Sometimes our attention narrows. These explanations may feel quieter than dramatic theories, but they are often closer to the truth. As astronomers continue to watch the sky, new objects will keep appearing. Some will be familiar. Others will feel strange. Each discovery will add a piece to a much larger picture, one that grows slowly over time. When we step back and look at that wider picture, the sense of sudden change often softens. The sky has not become crowded overnight. We have simply opened our eyes wider than before, and in doing so, we are learning not just about space, but about how our own minds respond to the unknown, how easily meaning can form where there is only motion, and how calm understanding begins when we allow events to exist without forcing them into a single story that must lead somewhere definite. In the past, the night sky looked calm and mostly unchanging. Stars held their places, planets moved slowly, and only once in a while did a bright comet appear to surprise people. For most of human history, we believed space was quiet, steady, and mostly empty. That belief was not wrong because of poor thinking, but because of limited vision. We could only see what our eyes and simple telescopes allowed. Many objects passed nearby without ever being noticed, slipping through the darkness unseen. Space was always busy, but we did not yet have the tools to realize it. Everything began to change as telescopes improved. Early astronomers relied on hand-built instruments, narrow fields of view, and long nights of careful watching. Discoveries came slowly. Finding a new asteroid or comet could take months or years, and many were found only by chance. The sky felt familiar because we were only seeing a small part of what was truly there. Most small and distant objects remained invisible, hidden by distance, darkness, or motion too subtle to detect. Modern telescopes changed this relationship completely. Instead of staring at one small patch of sky, today's systems scan huge areas automatically. They do not get tired. They do not blink. They work every clear night, recording millions of points of light and comparing them to past images. Anything that moves, brightens, or shifts is flagged for closer study. This constant scanning has revealed a sky that is far more active than anyone once imagined. One of the biggest changes came from wide-field survey telescopes. These instruments are designed not to look deeply in one direction, but to look broadly across the sky. They take repeated images of the same regions, sometimes every few nights, sometimes every few hours. By comparing these images, computers can spot objects that were not there before, or that have moved slightly between frames. This simple idea unlocked an entirely new view of the solar system. With these surveys, astronomers began finding near-Earth asteroids at an increasing rate. Objects that once would have slipped past unnoticed were now being detected weeks, months, or even years before close approaches. Many of these asteroids are small, harmless, and burn up if they enter Earth's atmosphere. But finding them matters, because it teaches us how common such encounters really are. What once felt rare is now understood as routine. The discovery of comets also changed. In the past, comets were dramatic events. A bright tail suddenly appeared, inspiring wonder and fear. Now, many comets are found long before they become visible to the naked eye. Telescopes spot them while they are still faint and far away, when sunlight has only begun to warm their frozen surfaces. This allows scientists to study how comets evolve, how their activity increases, and how they fade again as they move back into deep space. Modern telescopes have also expanded our ability to detect interstellar visitors. Objects like 3I Atlas move differently from typical asteroids and comets. Their paths are not bound to the sun. Instead, they pass through on open trajectories, arriving from one direction and leaving toward another, never to return. Without constant monitoring and precise tracking, such objects would pass unnoticed. Today, they stand out clearly against the background of stars because our instruments are finally sensitive and fast enough to catch them. Another major change came from improvements in digital detectors. Old telescopes relied on human eyes or photographic plates. These methods were limited and slow. Digital sensors can capture far more detail, measure brightness precisely, and operate at speeds humans cannot match. They turn light into data, and data into understanding. This shift allowed astronomy to move from careful observation to rapid discovery. Computers play a critical role in this new era. Modern telescopes do not work alone. They are paired with powerful software that analyzes images in real time. Algorithms search for movement, changes in brightness, and unusual patterns. When something new appears, alerts are sent across the world within minutes. Astronomers in different countries can follow up quickly, confirming or refining the discovery. The sky has become a shared, global project. This constant flow of information creates the feeling that objects are multiplying. In reality, the objects were always there. What has changed is our awareness. We are now seeing what was once invisible. This can feel unsettling at first. When people hear about many asteroids passing Earth or new objects entering the solar system, it can sound like something unusual is happening. But the truth is calmer. We are not under new threat. We are simply better informed. The increase in discoveries has also improved safety. Early detection means time. Time to calculate orbits. Time to rule out danger. Time to plan responses if ever needed. Instead of surprises, we now have forecasts. The sky has become something we monitor, not something that suddenly shocks us. This shift from fear to understanding is one of the most important outcomes of modern astronomy. Modern telescopes have also changed how we think about our place in space. Seeing so many objects moving through the solar system reminds us that Earth is part of a dynamic environment. Our planet travels through streams of debris, past wandering rocks, and alongside visitors from other stars. This movement is not chaotic or hostile. It follows the steady rules of gravity and motion. Understanding those rules brings a sense of order to what once felt random. As surveys continue to improve, even more objects will be found. New telescopes will scan deeper, wider, and faster. The sky will seem even busier. But with each discovery, fear fades and familiarity grows. What once felt like sudden danger becomes part of a known pattern. Modern telescopes have not made space more threatening. They have made it more understandable, more predictable, and ultimately more peaceful to observe. For most of human history, the night sky looked calm and unchanging. The stars rose and set, the planets wandered slowly, and everything else seemed fixed and distant. Because of this quiet appearance, it is easy to think that space has suddenly become more active, more crowded, or more unpredictable than before. In truth, the solar system has always been busy. It has always been full of motion, filled with countless rocks, ice fragments, dust trails, and wandering objects moving along invisible paths shaped by gravity. What has changed is not space itself, but our ability to see it clearly. Long before humans looked up with telescopes, asteroids and comets were already circling the sun. Leftover material from the birth of the solar system never fully disappeared. Instead, it settled into belts, clouds, and scattered populations that still move today. The asteroid belt between Mars and Jupiter contains millions of rocky bodies, some large, many small, all following their own paths. Beyond the outer planets lies the Kuiper belt, a wide region filled with icy objects that can become comets when nudged inward. Even farther out, the distant Oort cloud surrounds the solar system like a faint halo, holding trillions of frozen fragments waiting for the slightest gravitational push. These objects do not move randomly. They follow predictable orbits shaped by the sun and the planets. Some paths are stable for millions of years, while others slowly change. When a comet suddenly appears in the sky, it is not new. It has likely been traveling in darkness for billions of years, only now passing close enough to the sun for its eyes to warm and glow. When an asteroid passes near Earth, it is not invading our space. It has always been part of the solar system's flow, briefly crossing a region we happen to occupy. For much of history, we could not see these movements clearly. Early astronomers tracked planets with the naked eye and simple instruments. Bright comets were rare and dramatic, often seen as signs or omens because they appeared without warning. Smaller objects remained invisible. Even large asteroids went unnoticed unless they reflected enough light or passed very close. Space seemed empty not because it was, but because our vision was limited. In the last few decades, that vision has changed completely. Modern telescopes no longer rely only on human eyes looking through lenses. Automated survey systems scan the sky every clear night, taking thousands of images and comparing them to previous ones. Any point of light that moves slightly is flagged, measured, and tracked. Computers do the work of noticing motion that would have been impossible to spot before. This constant scanning has revealed a solar system that is alive with movement. Because of this, discoveries have accelerated. Objects that once slipped by unnoticed are now logged, named, and studied. Near-Earth asteroids are found weeks, months, or years before their closest approach. Small comets are detected early in their journeys inward. Faint objects from the outer solar system are identified long before they become visible to the naked eye. What feels like a sudden increase in activity is really a sudden increase in awareness. This change can feel unsettling at first. When people hear that several asteroids passed Earth in a short time, or that new objects are being discovered every week, it can sound like something has changed in space itself. But these passes were always happening. Earth has been sharing its neighborhood with passing rocks since it formed. The difference is that we are now watching closely, with tools designed to notice even the smallest movements. There is comfort in this realization. A busy sky does not mean a dangerous sky. In fact, seeing more objects often means greater safety. The more we detect, the fewer surprises remain. Objects that once could have arrived without warning are now tracked carefully. Their paths are calculated, updated, and shared openly among scientists around the world. Knowledge replaces uncertainty, and awareness replaces fear. The idea that space is crowded also reminds us that Earth is part of a larger system. Our planet does not exist in isolation. It moves through a stream of cosmic material, shaped by the same forces that guide everything else around the sun. Gravity gently steers objects past one another, sometimes pulling them closer, sometimes pushing them away. Most of the time, these interactions are slow and subtle, playing out over long periods far beyond a human lifetime. When interstellar objects like 3I Atlas pass through, they add another layer to this picture. They show that even beyond our solar system, stars exchange material. Our sun is not sealed off from the galaxy. It occasionally receives visitors from other systems, just as it may send fragments outward in return. These events are rare, but they are part of a much larger cosmic pattern that has been unfolding since the first stars formed. Understanding that space was always this busy helps calm the mind. It shifts the story from sudden danger to ongoing motion. It reminds us that what feels new is often just newly visible. The sky has not changed its behavior to surprise us. We have changed how carefully we observe it. Each new detection is not a warning, but a piece of a puzzle coming into focus. As telescopes improve and surveys grow more powerful, this sense of activity will likely increase. More objects will be found, tracked, and studied. The sky may seem even more crowded in the years ahead. But with that crowding comes clarity. Each discovery adds to a growing map of our surroundings, turning unknown darkness into familiar space. For those watching from Earth, this is a quiet success story. It shows how patient observation can transform fear into understanding. The solar system remains the same vast, moving place it has always been. The only real difference is that now, instead of being surprised by its motion, we are finally learning how to see it clearly, one faint point of light at a time. For most of human history, the night sky felt calm and unchanging. Stars rose and set in familiar patterns, planets wandered slowly, and anything smaller remained invisible to the naked eye. Even when telescopes arrived, discoveries were slow and rare. A new comet might appear once in a lifetime, and an asteroid was something most people never thought about at all. Today, that experience feels very different. New objects seem to be announced every week, sometimes every day. It can feel like space itself has suddenly become more active, but what is really changing is the way we look, the speed at which we work, and how closely the world's scientists are now connected. One of the biggest reasons discoveries are accelerating is that modern astronomy no longer relies on chance sightings or individual observers scanning the sky by hand. In the past, astronomers often focused on small areas of space, studying specific stars or planets one at a time. If something unexpected passed through a different region, it could easily be missed. Now, large survey systems are designed to sweep across huge portions of the sky automatically, night after night, without getting tired or distracted. These systems do not search for one special object. They record everything they see, quietly building massive libraries of images that can be examined in detail. Powerful computers play a key role in this change. When a telescope captures an image today, that picture is instantly compared to earlier images of the same region. Software looks for anything that has moved, changed brightness, or appeared where nothing was seen before. A faint dot that shifts slightly from one frame to the next may be flagged as a new asteroid. A fuzzy glow that grows brighter could be a comet beginning to wake up as it approaches the sun. This process happens far faster than a human ever could, often within minutes of the image being taken. What once required weeks of careful study can now happen almost in real time. Automation has also reduced human error and expanded coverage. Telescopes can now operate all night, every clear night, without needing someone at the controls. They adjust their aim automatically, respond to weather conditions, and follow carefully planned schedules that maximize how much sky they can scan. Some systems work together across continents, handing off observations as Earth rotates. When night ends in one country, it begins in another, and the sky continues to be watched without interruption. This constant attention makes it much harder for objects to slip by unnoticed. Another important factor is sensitivity. Modern detectors are far more capable than those used even a decade ago. They can pick up extremely faint objects that reflect very little light. Many of the asteroids and comets being discovered today are small and dim, the kind that would have been completely invisible to older instruments. These objects were always there, moving quietly through the solar system, but our tools were simply not strong enough to see them. As sensitivity improves, the population of known objects naturally grows, giving the impression of a sudden increase. Speed is also increased by how data is shared. In earlier times, an astronomer might discover something and then spend days or weeks confirming it before telling others. Today, discoveries are often posted to shared databases almost immediately. Scientists around the world can access the same information, confirm findings with their own observations, and refine calculations together. This global collaboration means that new objects are identified, tracked, and understood much more quickly than before. One telescope might spot something, another might confirm its path, and a third might analyze its composition, all within a short window of time. The rise of artificial intelligence has begun to push this process even further. Machine learning systems are now being trained to recognize subtle patterns in data that humans might overlook. They can learn the difference between noise, camera errors, and real moving objects with impressive accuracy. As these systems improve, they help reduce false alarms while increasing the number of genuine discoveries. They also free human researchers to focus on interpretation rather than detection, allowing science to move forward more smoothly and efficiently. Funding and international interest have played a role as well. Concerns about planetary defense have encouraged governments and space agencies to invest in sky monitoring programs. While the goal is safety, the result is a dramatic increase in the number of objects we know about. Dedicated efforts to find near-Earth objects mean that surveys are tuned specifically to look for moving bodies, not just distant stars. Every improvement in these systems adds to the steady stream of new discoveries. Public interest has also helped accelerate progress. Space exploration, asteroid missions, and high-profile discoveries have captured attention and inspired new projects. When the public is curious, funding follows, and when funding follows, technology improves. This creates a cycle where better tools lead to more discoveries, which lead to more interest, which then leads to even better tools. Over time, this cycle speeds up the pace of science in a way that can feel overwhelming if you are not used to it. It is important to remember that acceleration does not mean chaos. Even though discoveries are happening faster, they are not random or uncontrolled. Each new object is carefully catalogued, its path calculated, and its behavior studied. The growing list of known asteroids and comets represents increased knowledge, not increased danger. In fact, knowing about more objects makes the solar system feel safer, not more threatening, because fewer things remain hidden. From a human perspective, this rapid pace can create a sense of urgency or unease. News headlines may stack one discovery on top of another, giving the impression that something unusual is unfolding. But from a scientific point of view, this is a natural result of improved observation. It is similar to turning on a brighter light in a dark room. Suddenly, you see details that were always present but previously invisible. The room has not changed, only your ability to see it clearly. As discoveries accelerate, they also become more ordinary to the scientists who study them. Finding a new asteroid is no longer a rare event but part of a daily routine. This familiarity helps keep reactions calm and measured. Researchers understand that most objects follow predictable paths and pose no threat. Their focus remains on careful measurement, long-term tracking, and steady analysis rather than dramatic conclusions. This steady, quiet progress is easy to overlook because it lacks spectacle. There are no sudden flashes or loud alarms, just a continuous flow of data and patient work. Yet this is exactly what makes modern discovery so powerful. It is not driven by fear or excitement, but by consistency. Night after night, the sky is scanned. Image after image is compared. Pattern after pattern is recognized. Over time, this builds a clearer and more complete picture of the space around us. As software improves, as telescopes become more sensitive, and as global cooperation deepens, discoveries will likely continue to accelerate. Not because space is changing, but because our relationship with it is. We are learning to observe without interruption, to share without delay, and to understand without rushing to conclusions. While headlines move fast and speak loudly, the work of science moves in a very different way. It moves slowly, carefully, and often in near silence. When a new object is discovered in space, the first response from scientists is not excitement or fear, but patience. They gather data. They check it twice. They ask simple questions and look for clear answers. This calm process can feel boring compared to dramatic news alerts, but it is exactly what keeps us safe and informed. In recent weeks, as reports about new objects, near-Earth asteroids, and interstellar visitors filled social media and news sites, scientists were quietly doing what they always do, measuring positions, calculating orbits, and comparing new information with decades of past observations. Loud headlines are designed to catch attention. They use strong words like mysterious, unknown, or unprecedented because those words make people stop scrolling. This does not mean the information is always wrong, but it is often incomplete. A headline may focus on the most unusual detail while leaving out the context that makes it understandable. Science works in the opposite direction. Context is everything. A single image, a single data point, or a single discovery does not mean much on its own. Scientists want to know how it fits into the larger picture of how the solar system works. They compare it to thousands of similar objects already catalogued. They look for patterns that repeat, not events that happen once. When astronomers detect a new object, the first step is usually confirmation. Is it real, or is it an error in the data? Modern telescopes are powerful, but they still produce noise. Reflections, sensor glitches, and even satellites can appear as moving points of light. Scientists take multiple observations over time to make sure an object is truly there. Only after confirmation do they begin to describe what it might be. This process rarely makes headlines, but it is the foundation of reliable knowledge. Without it, every bright pixel in the sky could become a breaking news story. Another difference between calm science and loud headlines is how uncertainty is handled. Headlines often treat uncertainty as danger. Phrases like "scientists don't know" are presented as warnings. In science, uncertainty is normal and expected. Not knowing something yet does not mean something is wrong. It means the process is still working. Scientists are comfortable saying they need more data, more time, or better measurements. This patience allows them to avoid false conclusions. It also prevents unnecessary fear. Most objects detected near Earth turn out to be small, distant, and harmless. That conclusion comes not from guessing, but from careful tracking over days, weeks, and sometimes months. The way scientists communicate among themselves is also very different from how news spreads online. Research papers are written in plain, careful language. Claims are limited to what the data supports. If there is doubt, it is clearly stated. Other scientists then review the work, question it, and try to reproduce the results. This process, called peer review, is slow by design. It filters out mistakes and exaggeration. By the time information reaches official space agencies or public databases, it has usually passed through many layers of quiet checking. Headlines, on the other hand, often appear within minutes of a discovery, long before this process is complete. This difference in speed creates tension. The public wants answers right away. Scientists want accuracy. When those two timelines clash, misunderstandings can grow. A headline might suggest that objects are multiplying in a sudden and dangerous way, while scientists see a steady stream of discoveries that match long-standing models. The sky has always been busy. What has changed is our ability to see it clearly. Modern surveys detect objects that older telescopes simply missed. From a scientific point of view, this is a success story. From a headline point of view, it can be framed as something alarming. Calm science also focuses on probability rather than possibility. Almost anything is possible in theory, but what matters is how likely it is. Headlines often highlight rare scenarios because they are interesting. Scientists calculate odds. They ask how often something like this has happened before, and how often it is expected to happen again. In the case of near-Earth objects, decades of data show that most pass safely by, many at distances far greater than the Moon. When an object appears closer, it receives more attention from scientists, but that attention is analytical, not emotional. Another quiet aspect of science is how corrections are handled. If early data suggests something unusual, scientists may later revise their understanding as better measurements come in. This is not a failure. It is a sign that the system is working. Headlines, however, may not always follow up with the update. The initial dramatic story spreads widely, while the calmer correction reaches fewer people. This can leave the impression that scientists are confused or hiding information, when in reality they are refining it. The truth becomes clearer over time, even if it is less exciting than the first version. There is also a human side to this contrast. Scientists are people who spend long nights observing the sky, writing code, and checking numbers. Their work requires focus and calm thinking. Panic and excitement are not helpful tools when calculating orbits or predicting motion years into the future. The culture of science rewards careful thought, not bold claims. Headlines reward attention. Both serve a purpose, but they are not the same thing. Understanding that difference can help viewers feel more at ease when reading about space events. For viewers watching a documentary for sleep, this calm approach matters even more. Loud headlines can follow us into the night, keeping the mind alert and restless. Calm science invites a different response. It reminds us that the universe operates under consistent rules, even when it appears complex. Objects move along paths shaped by gravity. Discoveries follow patterns shaped by technology and effort. There is comfort in knowing that professionals around the world are quietly watching the sky every night, not with fear, but with curiosity and care. As more discoveries are made and more headlines appear, the contrast between noise and knowledge will likely grow. Learning to listen for the quieter voice can make a difference. That voice speaks slowly, explains patiently, and leaves room for uncertainty without turning it into worry. It tells us that space is active, not chaotic, and that understanding comes step by step, observation by observation, measurement by measurement. Even when the world outside feels loud and urgent, the science itself continues at its steady pace, focused on clarity rather than drama, on evidence rather than emotion, and on building a reliable picture of our place in a sky that has always been full of motion and light. Every object that moves through space carries a quiet record of where it came from and how it has changed. Asteroids and comets are not just rocks drifting in the dark. They are small pieces of history, formed long before Earth had oceans, trees, or people. When scientists study these objects, they are not only tracking motion. They are reading stories written in ice, dust, and stone, stories that began when the solar system was young and still taking shape. In the earliest days of the solar system, the sun was surrounded by a wide, spinning disk of gas and dust. Inside this disk, tiny grains slowly stuck together, forming larger and larger pieces. Some of those pieces became planets. Others never grew that large and remained as leftovers. Asteroids and comets are part of that leftover material. They are time capsules that have stayed mostly unchanged for billions of years, quietly orbiting the sun or resting far away in cold, distant regions. When we observe an asteroid, we are seeing material that never became part of a planet. Its surface may still hold the same minerals that existed before Earth fully formed. Some asteroids contain metals that sank deep into planets like Earth, while others are rich in carbon and organic compounds. By studying these differences, scientists learn how materials were sorted and mixed during the early days of planetary building. Comets tell a slightly different story. They usually come from colder regions far from the sun, where ice could survive. Their frozen surfaces trap gases and dust from the early solar system, sealed away like a deep freeze. When a comet moves closer to the sun, its ice warms and releases gas, creating a glowing coma and tail. That glowing cloud is not just beautiful to see. It gives scientists clues about the chemical makeup of the early solar system, including water, carbon compounds, and simple molecules that may have helped life begin on Earth. Some scientists believe comets played a role in delivering water to our planet long ago. Early Earth was hot and violent, shaped by constant impacts. Comets crashing into the surface may have brought ice that melted into water, helping fill the oceans. While this idea is still being studied, each new comet observed adds another piece to that puzzle, helping scientists test how likely that process may have been. Asteroids also help scientists understand how planets interact with one another over time. Their paths change due to gravity from larger bodies like Jupiter and Saturn. Some asteroids are pulled into stable groups, while others are nudged into new orbits that bring them closer to the inner solar system. By tracking these movements, scientists learn how gravity shapes the long-term structure of planetary systems, not just here, but around other stars as well. When an interstellar object like 3I Atlas enters our solar system, it brings a lesson from beyond our neighborhood. These objects formed around other stars, under different conditions, with different chemical mixes. By comparing them to local asteroids and comets, scientists can see which features are common across the galaxy and which are unique to our solar system. This helps answer a larger question: is the way our system formed typical or rare? Each new discovery also teaches scientists about change. Space may feel slow and steady, but these objects show that it is always moving. Collisions break asteroids apart. Sunlight alters surfaces. Gravity reshapes paths over millions of years. By studying these processes, scientists learn how planetary systems evolve, not in dramatic moments, but through long periods of quiet motion. There is also a lesson in scale. Asteroids and comets remind us that planets are not isolated. Earth exists within a wide network of moving material. Most of it passes by unnoticed, quietly and safely. Understanding this helps replace fear with perspective. Space is not suddenly becoming more dangerous. We are simply learning to see it more clearly. These objects also teach patience. Scientists often spend years observing a single asteroid or comet, gathering small bits of data that slowly build a clear picture. There are no quick answers. Each measurement adds a tiny piece to a much larger understanding. This slow, careful work reflects how science truly progresses, not through sudden discoveries alone, but through steady attention. There is something deeply human about this process. Long before modern science, people watched the sky and wondered about the lights moving overhead. Today, we still feel that same curiosity, but we now have tools that allow us to ask better questions. Asteroids and comets become bridges between ancient wonder and modern knowledge. They also teach humility. Even with powerful telescopes and computers, there is still much we do not know. Each object observed often raises new questions. Why does one asteroid spin faster than another? Why does a comet release certain gases but not others? Why do some objects follow strange paths? These questions remind us that understanding is always incomplete, and that learning is a continuous process. As more objects are discovered, patterns slowly emerge. Scientists begin to see families of asteroids with shared origins. They identify comets that may have broken apart from larger bodies long ago. These patterns help reveal the hidden history of collisions and movements that shaped the solar system long before humans existed. There is also a lesson about connection. The material in asteroids and comets is the same material that makes up planets, moons, and even our own bodies. The elements found in these objects are part of the same cosmic supply that formed Earth. Studying them is, in a quiet way, studying ourselves and our place in the universe. In the end, these wandering objects teach us that space is not empty or silent. It is active, layered, and full of history. Every asteroid passing by, every comet lighting up near the sun, carries information that helps us understand where we came from and how the solar system continues to change. The sky above is not delivering warnings or threats. It is offering lessons, slowly and patiently, for those who take the time to watch and listen. Researchers are now stepping back and asking a careful, thoughtful question, one that does not demand a quick answer. As more objects appear in discovery lists and news reports, it is natural to wonder whether something has truly changed in the skies above us, or whether our tools have simply become better at seeing what was always there. This question sits quietly at the center of modern astronomy, and it shapes how scientists interpret every new detection. Rather than rushing to declare a new era of danger or surprise, researchers prefer to slow down, compare long-term data, and look for patterns that hold steady over time. For most of human history, the night sky appeared calm and mostly unchanging. Stars rose and set, planets wandered slowly, and comets arrived only rarely, often without warning. In truth, the solar system has always been filled with motion. Countless rocks, icy bodies, and fragments travel along invisible paths shaped by gravity. They pass near planets, cross orbits, and sometimes vanish back into the dark. The difference today is not the number of objects moving through space, but the clarity with which we can now observe them. Modern detection systems work every clear night, scanning the same regions of sky again and again. They compare new images with older ones, looking for tiny points of light that shift position. What once required patient human eyes now happens automatically, guided by software that never gets tired. Because of this, objects that would have slipped by unnoticed 10 or even 5 years ago are now added to catalogs within hours. From a scientific point of view, this creates the feeling of acceleration, even if the underlying reality remains steady. When researchers analyze detection rates, they look beyond daily or weekly spikes. A cluster of discoveries in 1 month may reflect good weather, upgraded equipment, or a new survey coming online. To understand whether a true trend exists, scientists stretch the timeline. They examine years of data, adjusting for changes in technology and coverage. When they do this, a clearer picture begins to form. In most cases, the apparent increase in objects closely matches improvements in how often and how deeply the sky is observed. Still, science leaves room for curiosity. There are open questions about whether subtle changes in orbital dynamics, gravitational nudges from planets, or long-term cycles in the outer solar system could influence how objects drift inward. These ideas are studied carefully, tested through models and simulations rather than headlines. The goal is not to confirm a dramatic story, but to understand the system as it truly behaves. Interstellar visitors like 3I Atlas add another layer to this discussion. They are rare, but not impossible. As surveys grow more sensitive, it makes sense that we would notice more of them passing through. Their discovery does not mean the galaxy has suddenly become more active. It means our awareness has expanded. Each detection gives scientists a chance to refine estimates, helping them predict how often such visitors arrive and how they move through unfamiliar territory. What matters most is the tone with which this information is shared. In science, uncertainty is not a weakness. It is an honest space where learning happens. Researchers are comfortable saying we are still studying this or the data is not yet clear. This calm approach stands in contrast to louder interpretations that turn every new object into a sign of change or threat. The scientific process moves forward quietly, step by step, guided by evidence rather than emotion. For viewers and listeners, understanding this difference can bring peace of mind. A busy discovery list does not mean the sky has become more dangerous. It means humanity has become more attentive. The same sky that sheltered past generations still surrounds us, governed by the same physical laws. The motion has always been there, steady and patient, waiting to be noticed. As you listen to these stories, it helps to remember that attention does not equal alarm. Watching carefully is a sign of maturity, not fear. Each new object logged into a database strengthens our understanding of where we live and how our cosmic neighborhood works. It allows future generations to plan, to prepare, and to appreciate the vastness above without unnecessary worry. In the end, whether we are seeing the start of a new trend or simply the results of better observation, the message remains gentle. Space is active, complex, and full of quiet movement. Scientists are listening, measuring, and learning, just as they always have. And as you rest, you can let these thoughts drift by like distant stars, knowing that curiosity and calm can exist together, that knowledge grows steadily, and that paying attention to the universe does not require fear, only patience, wonder, and the willingness to look up and keep listening.